Again, welcome to UConn. Thank you for coming. And this is a course, a very quick tour of arithmetic statistics. All right, so let me just check one more time. This is looking fine. All right, so what is arithmetic statistics? So arithmetic statistics is a term that has been started to be used sort of in the recent past, but it describes something that has been done for quite a while. And I'm going to give you some sort of like historical tour of arithmetic statistics from things that we as mathematicians were doing 200, 300 years ago, to things that are being done now. And during the research conference, people like Ila Varma or Robert Lemke Oliver, they will talk about things that are sort of like what people think of arithmetic statistics nowadays. So what we want to do in arithmetic statistics is to count number theoretic objects. In principle, with number theoretic objects, you want to find them. You want to see if they exist and find them all. But we want to think about families where there may be infinitely many, and we know there are infinitely many, but now we want to give a sense of size and then count so many number theory objects up to that size, up to a given size. So number theoretic objects that we're interested in, for instance, well, prime numbers, twin prime numbers, Wieferich primes, etc. Something that seemingly a little bit different, but during the course of the 4 lectures, I'll try to do a path from all of these things, one to the other. So binary quadratic forms, binary cubic forms, etc. Those are important for a number of reasons. Number fields. We also have number fields attached to number fields that are other things that are of number theory interest. The class group of a number field, etc. Zeta functions, L functions, elliptic curves. Attached to elliptic curves, there is the Mordell-Weil groups, and then torsion subgroups of elliptic curves, ranks, Tate-Shafarevich groups. All these things are things we will be interested in, and we will describe very, very briefly during these lectures. So what questions are we trying to answer? We are going to fix a number theory object or family, and we're going to ask ourselves a number of questions. First of all, do they exist? I can give you some description of a number theory object I'm interested in, and I don't know if there are any at all. Maybe I know, you know perfectly well, that prime numbers, since Euclid, we have a proof there are infinitely many prime numbers, right? But now that I know they exist, I want to know, are there finitely many or infinitely many such objects? Maybe I don't know, I can't prove that there is a single one. But is there a single one? If so, are there finitely many or infinitely many of them? Can we parameterize these objects in families? Some of these objects, number theory objects, class groups, or number fields, we're interested in some aspect of these objects. For instance, for number fields, we might want to look at all degree 2 number fields, all the quadratic number fields, all the degree 3 number fields. We might want to parameterize all the number fields that are cubic, and the Galois group is of order 3. That's a family of interest. But once you have those, there are databases of number fields, but we would like to know how many of those are there. We have a way to size these objects, and we want to know how many of those are there up to this size. So in this number theory object, is there a notion of size or of height? How many objects are there up to a given height? Can I give you an asymptotic of how many objects are there up to a given height? How many objects are there relative to another number theory object? We'll see some examples of those. So for instance, we'll start with prime numbers, and prime numbers, you can order them by their absolute value. Yeah, that's not an absolute discriminant. That's why I wrote. Value. Okay. These notes, by the way, the slides, I will post them after the lecture. That's why they're not posted now, because I'm going to fix things like that along the way, and then I'm going to fix those, and I will be putting them up on the website next to my name in the page for the summer school. So we want to know prime numbers. We can order them by their absolute value. And then there are families, like, for instance, 1 mod 4. The primes are 1 mod 4. But as I said, sometimes we want to compare with other families. The primes that are odd, they're 1 or 3 mod 4. So we will compare them with families of primes that are 3 mod 4. Are there more or less primes that are 1 and 3 mod 4? Are there infinitely many primes that are 1 mod 4? And so on. Twin primes, that's a family where we conjecture that there are infinitely many such objects, but we don't know. But that doesn't scare us from trying to conjecture how many there should be. What's the asymptotic formula for how many twin primes are there up to a given height? And where do those formulas come from? If we don't even know there are infinitely many, how do you dare to conjecture that not only there are infinitely many, there are asymptotically exactly these many? How does that come about? We'll talk a little bit about that today. Primes of the form, that n squared plus 1 is a polynomial, and those are primes that are values of polynomials. That we don't know anything about that either. We don't know that there are infinitely many primes that are n squared plus 1. Or if you take any polynomial that is a quadratic or a higher degree, we do not know how to prove that there are infinitely many primes of that form. But yet, we have very precise conjectures of how many of those primes there should be. With theoretic primes such that 2 to the p minus 1, that's also a typo, that's 2 to the p minus 1 by Fermat's little theorem, that's divisible by p, but is it possible it's divisible by p squared? That's a theoretic prime. Are there infinitely many of those? We know 2. But we expect there are infinitely many. How so? Like what kind of heuristic argument do we have to expect that that's true? Okay, binary quadratic forms. Apparently a very different topic, but not so much. If you look at the previous slide, where we were talking about primes of the form p equals n squared plus 1. P is in there a sum of 2 squares, n squared and 1 square. So you can talk about primes that are, what primes are the sum of 2 squares. That's a binary quadratic form, x squared plus y squared. And there is a nice transition from primes to talking about binary quadratic forms. We can order them by their discriminant. And then we can do the same kind of line of questioning. Are there infinitely many such forms? Sure. How many are there up to a given discriminant? Can we parameterize them in families that make sense in one number theoretic way or another? And we'll do that. How about higher order binary forms, like cubic binary forms? And where do those come up? So there is some very recent developments. The work of Manjul Bhargava connects these forms. Well, long ago, there was connections between binary quadratic forms and ideal class groups, but now we have all sorts of connections also with cubic forms and other forms with number fields of certain types and class groups and very interesting connections. What about number fields? So number fields, they also have a natural size, have the absolute value of their discriminant. If you've had some number theory, then you know that discriminant measures, for instance, how many bad primes are there, what are the primes that ramify in that number field. So we can count number fields up to a given discriminant, and then, as I said, we want to know also how many number fields are there up to a given discriminant with some fixed element, some of fixed degree or a fixed Galois group, etc. Out of those number fields, we're very interested in their class groups, just to know how far the ring of integers is from being a unique factorization domain or a PID. And so we're interested to know, like, what kind of class groups can we find? For instance, we'll talk about class groups of imaginary quadratic fields and what's known. Elliptic curves. So elliptic curves are plane curves. So there's some smooth projective curves of genus 1. And there's a lot of work being done on elliptic curves. Last 2 years ago, I gave a mini course was on elliptic curves. This year, Eric Wallace will be giving a course on elliptic curves over finite fields. And we can order elliptic curves in a couple of ways. We can order them according to their discriminant. But there's another way to order elliptic curves according to their conductor. So you can try to count up elliptic curves by the discriminant, by the conductor, and sometimes you get different answers depending how you count. There will be another way that this will come up. Just talking about, even talking about primes, this will come up that sometimes you want to change a little bit how you count things, and then you see different statistics about how many of those objects are there up to a size. So an elliptic curve, there is the main theorem of elliptic curves is the Mordell-Weil theorem. Over Q is just the Mordell theorem that says that the set of rational points is a finitely generated abelian group, and then from the structure theory of finitely generated abelian groups, there is a finite torsion, a finite subgroup of points of finite order, and then a free part. And then we want to study, okay, when do we see each one of those? When will we see different torsion structures? How many are there up to a given discriminant? When we will see different ranks? We don't know if the rank can be arbitrarily high, but we can try to start making heuristic models about when should we expect to see an elliptic curve of rank 29. The highest we know is rank 28. Should we expect an elliptic curve of rank 29? If so, where? How far do we have to go looking for one of those? And then the Tate-Shafarevich group is sort of the analog of the class group for number fields, in that it measures a failure, in this case the failure of not being of the local to global principle. So what spaces, some spaces that have points locally everywhere, whether they have a point globally or not, and it's sort of like the only obstruction for what we hope is an algorithm to find all the points on the elliptic curve. And if the Tate-Shafarevich group is finite, then we have sort of an algorithm to find all the points. So we are trying to also model and understand what kind of Tate-Shafarevich groups do we expect to find by height of elliptic curves. Okay. So that's sort of like the overview of what we're going to do. And what we are going to do in these lectures is I'm just giving you some examples of how one goes about doing these things, of doing some like of these wild conjectures, how do you come up with some heuristics, and then also some things that are known and how you go about proving some of the things that are known. So we're going to start with prime numbers. So we start with a familiar territory. Here's a few prime numbers. And if you start looking at prime numbers, there is a lot of like little patterns that appear, but sort of like the larger pattern of like where are the prime numbers, that's quite mysterious and sort of like hard to get to. And in fact, people such as Euler said that, well, mathematicians have tried in vain to this day to discover some order in the sequence of prime numbers, and we have reason to believe that it is a mystery into which the mind will never penetrate. And yet, 20 years later, somebody penetrated into that mystery, which is sort of like the prime number theorem. So Gauss, Legendre, and Dirichlet formulated three different versions of what we now know as the prime number theorem. And this is, to me, the very first example of arithmetic statistics, in that, as Euler said, it's very hard to penetrate and to just give some formula. Maybe what Euler was hoping was a formula, closed formula, would tell me what the nth prime is exactly. That is very hard to get to. But what you can do is that, okay, I'm not going to concentrate on one prime exactly of size, this size, but I'm going to look at all the primes and somehow I'm going to be able to give you a statistic, an asymptotic for how many primes you should expect up to any given x with some error. Keith?
It's not Legendre.
Very good observation. So these are three pictures of Legendre, Gauss, and Dirichlet, and maybe the audio didn't pick up that Keith said that's not Legendre. And that is not Legendre. So for a long time, Legendre was misrepresented by that picture of Louis Legendre, who was some politician that had nothing to do with our Marie Legendre, who was so not that guy. And this is actually the only surviving portrait of Legendre. So maybe we're better off with the other one. So if you see that picture of Legendre now, if I had a time machine, that's the first person I would go visit. Okay, so again, the prime number theorem tells you that, in a sense, yes, the prime numbers are very hard to penetrate into the mystery of where the prime numbers are, but in average or statistically, there is something to it that we can say in some very interesting theorems. These theorems, this notation is that says that pi of x, the number of primes up to x, is asymptotic to x over log x. So what that means, that symbol, I will write it a bunch of times, is says that the limit as x goes to infinity of the two functions is 1. That it does not say that the two functions are very close to each other, so that the pi of x is well approximated by that function. It just says that they're asymptotic and that the limit goes to 1. There is a big error that accumulates, and the error grows to infinity, but it's small enough that asymptotically the limit of one and the other is 1. So the order of magnitude is right. And you can do much better than this, and you can give a sense of what that error is. So you can certainly improve this arithmetic statistical theorem. But that is the spirit of the theorems that we want to, or hopefully the theorems one would want to prove is of this sort. Those are Hadamard and Vallée-Poussin, who were the two mathematicians who simultaneously proved the prime number theorem, which you can see there, like their lives are like 1 year off from each other, and then they proved this big theorem the same year in 1896. Okay, so here's a table, as I said, of the approximations of pi of x. So here's pi of x up to 10 to the 10, the exact count of prime numbers. That's how much x ln x gives you. X ln x minus 1, that is Legendre's format for the prime number theorem. And that is another format for the prime number theorem. That's what's called the logarithmic integral, which is this is sort of like Dirichlet's form for the prime number theorem. And then you can see that this logarithmic integral is pretty nice, even as an approximation. But what you can prove is that it's all three are asymptotic. But this one sort of like it's a little bit closer in terms of the data. Okay. So let's try to conjecture ourselves the prime number theorem. So I don't know if you have a sense of why would that function be a priori. Maybe you've seen it enough times that now it sounds familiar. But if you didn't know the prime number theorem, if you were Euler, how would you come up with, or if you were Gauss and you were actually going to do it, Euler didn't do it, but if you were Gauss and you were going to conjecture such a thing, where would you start? So let's try to conjecture that theorem. Okay, so our first assumption is that there is a mathematical law, that Euler was wrong, and there's a mathematical law that explains where the primes land. And by a mathematical law, we are going to want some probabilistic law. In that, so there are two assumptions, two running assumptions. For large n, we have that the number of primes up to n is given by an integral of a function. So this wx is a probability density function. So if you've seen some probability, that's the density function. If I integrate the density function, then I get how many of those events are actually happening. Okay? And also that for large x, or x larger than some increment, we have that when you increment the number of primes, or the bound, it is really a good approximation is given by wx times delta x. Okay? That's just my basics. And then all I want is try to conjecture what wx would be without, I'm not trying to prove anything right now, although much of what I'm going to say can be formalized and get pretty close to the prime number theorem. I'm really interested in finding out if there was such a law, what would the law be? And then maybe I'll try to prove it later on, okay? All right, so first of all, so what we're going to do is actually write a formula for the log of n factorial in two ways. So the first formula that I'm going to give you is that log of n factorial is asymptotic to n times log of n. This one I'm not going to prove, but it's an exercise. I will be posting also after the lecture a piece of paper, a PDF with exercises that will be updating as I go on with my lectures and adding more exercises. So try to prove yourselves that log n of n factorial is asymptotic to n log n. Okay, and now we're going to give a second formula for log of n factorial in terms of prime numbers. Okay? All right, I'm going to need some notation, and the notation that I need is the p-adic valuation of an integer. So the p-adic valuation is the largest non-negative integer such that p to the new p of a divides a. In other words, if I can write a as a power of p times something that is relatively prime to m, that power of p, new pa, that's the p-adic, the p-adic valuation of a. Okay. You can also check that the p-adic valuation of a product is the sum of the p-adic valuations, and therefore we have that the p-adic valuation of n factorial will be the sum of the p-adic valuations of the numbers 1 through n. And I'm going to define two numbers. The first number for every prime on k is how many numbers are there from 1 to n that are divisible by p to the k. And the second number are those numbers from 1 to n that are exactly divisible by p to the k. Yes?
In the previous slide, can you just go back for a second? Yeah. So when you say pi of n, and is it like part A you mean asymptotic, or because generally part A, pi of n, is it asymptotic you mean, or?
I mean, I do mean an approximation in that not just asymptotic, but it's some good approximation of it. So let's say asymptotic in that the error is less than, yes, let's say asymptotic. But I'm not trying to say anything like very precise at this time. So I do mean that I'm hoping, I mean, if I'm not going to be precise, I'm hoping for an equality of some sort. It may be the number on the left is an integer, the number on the right is going to be some real number. You can put a floor in there or something. But
sometimes, I mean, the symbol is used like less than, and greater than, that kind of symbol sometimes they use.
Yeah, so I'm using a couple of symbols. So here, this is really approximately, that's much larger than.
Okay.
Because as I said, I'm not trying to be very precise at this time. Okay. All these things can be done precisely, and then I would need more precise symbols. Okay. So here are the numbers that I'm trying to define. Again, the number nk is the number of numbers up to n that are divisible by p to the k, not exactly just divisible. Mk are those that are exactly divisible by p to the k. Therefore, well, if you think like what is this going to be, I think nk is the floor of n over p to the k. So it's approximately n over p to the k. and mk are those numbers that are divisible by p to the k, but not by divisible by k plus 1, so I have to subtract those, and therefore mk is approximately, well, it's going to be the floor of one minus the floor of the other, so it's n over p to the k minus n over p to the k plus 1. And I'm not sure there is a hence here. This is not following at the moment. The p-adic valuation of n factorial from the definitions of the mk will be, well, I want to know how many primes are just dividing n factorial exactly once, how many times, how many numbers will there be that are dividing up to n, how many numbers are there that p divides, p squared divides that number, how many numbers are there that p cubed divides that number, and there will be the valuation that you get from each one of those. So the numbers that p only divides once, there will be contribution of 1 in the valuation. The numbers that are the p squared divides exactly, there will be a 2 contribution in the valuation, and so on. So that gives you the valuation of n factorial, and then if you use the approximations we've come up with, so the valuation of n factorial will be that formula. m1 is by almost definition is n1 minus n2 plus 2 times n2 minus n3, and so on. And if you simplify that sort of telescopic sum, you get that sum is n1 plus n2 plus n3, and so on. And approximately each one of those is n over p plus n over p squared plus n over p cubed, and so on. Now here I'm being very vague in that there is some difference between, you remember n1 was supposed to be the floor, so there's some like fractional part that I'm forgetting about, and I'm hoping that that's not adding to too much, but that's approximately that value, and then you can take a common factor of n over p, and you get that product, and that sum, which is an infinite sum here, but at some point all those mk's would be 0, so it would be really a finite sum, but I'm going to leave it as an infinite sum. If it's an infinite sum, hoping also that the error, I'm not adding too much more, the sum of these numbers will be p over p minus 1, so n over p times that gives me n over p minus 1. So the p-adic valuation of n factorial is approximately n over p minus 1. And again, you could do better and try to narrow down the error of that approximation. Okay, so now we have a formula for n factorial, for the logarithm of n factorial, which is as follows. We have the logarithm of n factorial. I can write n factorial as a product of primes, so prime factorization of n factorial, and because the logarithm of a product is the sum of the logarithms, I can do that, and then simplify that exponent is approximately n over p minus 1, and that exponent comes out of the logarithm to get me that formula for log of n factorial. All right? And then we've deduced two different asymptotics for log of n factorial. The one on the right I haven't really proved that is an asymptotic, but I think that should be about the right size of log of n factorial. And again, you can go carefully and see that those errors don't amount to much, and in the limit it would be asymptotic. So I have that n log n is asymptotic to the log n factorial, and also asymptotic to that formula in terms of primes. Great. So if you set n equals x, then in both sides of log of n factorial, if you equal those two sides, then there is going to be an x that cancels out. And what I get is the log of x is asymptotic to that sum of log p over p minus 1. And that sum, it kind of looks like some sort of Riemann sum. So let's interpret that sum as a Riemann sum. I'm going to break the interval from 2 to x into a number of intervals. It's small enough so that my mathematical law of the prime numbers kicks in, and I can apply that mathematical law. So if it is small enough intervals, then the difference, the number of primes in each subinterval will be approximately W of a number in that interval times delta of that number. Okay, delta x in this case is whatever length of a subinterval I've decided on, and then if the intervals are small enough, then if p is in one of those intervals, then p is like one of the numbers in the interval. So I'm picking the left-hand side of the interval. Okay, so when that tells me then is that log of x is approximately that asymptotic we found, and that asymptotic I can interpret it as a Riemann sum, and that Riemann sum will be again in turn approximated by a Riemann integral. So it tells me that log of x is approximately the integral from 2 to x of this density function times log t over t minus 1. Okay, so now, again, if you assume that that's an equality, now I could take derivatives and then try to figure out what wx is. So if you take derivatives of both sides, use the fundamental theorem of calculus, then you get that 1 over x is wx times log x, x minus 1. And therefore, we arrive that wx is like x minus 1 over x log x, which is approximately 1 over log x for large x. So it follows that, and it follows should be more or less in quotes. We haven't proved anything. That the prime counting function is asymptotic to the integral from 2 to x of 1 over log t dt. And it turns out that that is Dirichlet's version of the prime number theorem, that the prime counting function it is asymptotic to the logarithmic integral which is given as or that the weight function, the density function, is 1 over log x. Okay, so what we've done is we're not going to claim that we are as good as Dirichlet. All we've done is that if, and that is a big if in red letters, if there is a probability density function for the prime numbers, that's the one. It's 1 over log x, that's the density function of the primes. That doesn't mean that there is such a law. It just says if there was one, that's the one. Okay? Nonetheless, Dirichlet's theorem is true in that those two functions are asymptotic to each other for whatever reason. That doesn't mean it's giving you maybe some evidence that there is such a law. It's just saying that at least you can use this sort of like heuristic reasoning that the probability that one number x is prime is like 1 over log x. Okay? And that has been used in many settings to come up with other crazy heuristics and conjectures. So, for instance, Pierre de Fermat, he defined what we call Fermat numbers. So Fermat numbers are numbers of the form 2 to the 2 to the n plus 1. And those are Fermat numbers. If that number is prime, that's called Fermat prime. And he conjectured that there are infinitely many, or that there are all of them are prime numbers. And then actually now we believe the opposite, that there are only many Fermat primes, and in fact we might know them all. So if you look at, I put the pictures of Hardy and Wright there in their book on an introduction to number theory, an introduction to the theory of numbers, perhaps. An introduction to the theory of numbers, they say that it's very likely that there are only finitely many of them, and they give a heuristic reason based on our heuristic of how likely a number is of being prime. So here's the proof that there are only finitely many Fermat numbers, Fermat primes. There are infinitely many Fermat numbers, but primes should be rare. So if the Fn numbers behave as random numbers, then each one of them is prime with the chance 1 over log of that number. Okay? if that's so, I can do an expected value of how many I should find. So I'm going to do that. Then the expected number of how many I should find that are actually primes should be the sum of the probabilities that of each one of them being prime. So you can do that. If you add up the probabilities that each one of the Fermat numbers is prime, that's the sum that you need. And then the sum, if you substitute the value of fn, that's that. And then you can drop the 1, and then you get a sum of 1 over the log. And the exponent can come out multiplying. And then you just have a common factor of 1 over log 2 that comes out of the sum. And now that's a geometric sum that I can add up. So the sum of all that, it says that the expected value is less or equal to 2 over log 2. And that's about 2.8853. So that says that if it's true that we have such a density function for the primes, and it is true that the Fermat numbers behave just randomly, just jumping, that formula is jumping from number to number at a random pace, then there should be about 3 Fermat primes. Now that's false, because there are 5 at least. So there's the first 5 are primes, 3, 5, 17, 257, and 65,537. Those are primes, but we haven't found a single other prime, and we've gone not too far up, but there's a bunch of have been tested, and they are not primes. So that's that. So it doesn't give you, this is not approved by any means, but it gives you some sense that it, well, at the very least, the Fermat primes should be very rare, and perhaps just this is all of them. But again, we are far from approved because, well, we don't know that there is such a density function. The probability is really that it just fits Dirichlet's theorem, but we don't have that heuristic, sort of like a proof of that heuristic. Okay, how about twin primes? There are supposed to be, the conjecture says there are infinitely many prime numbers, such that p and p plus 2 are primes. Here's a few of them, and here is a table of how many twin primes are there up to x. Okay. So, are there infinitely many? Sure. Let's prove it again using our heuristic. So, if n and n plus 2 behave as random numbers, then the probability that both n and n plus 2 are going to be primes will be the product of the probabilities. If they are independent, if they are independent events, that n and n plus 2 are primes, okay? If those two things are independent, then the probability is just 1 over log n times log n plus 2. So I can add all the probabilities up, and what I get is the integral from 2 to x of 1 over log 2 squared, which diverges, okay? And you can prove that that diverges, so there should be infinitely many twin primes. Now, this is obviously false, because if n is even, n plus 2 is even, so these are not independent events. But you have to account for that, and you can account for that there are some small congruence relations. Well, for every prime, if n is 3 mod 5, then n plus 2 will be 0 mod 5 and will not be prime. So you can account for, okay, I'm going to have to take a proportion out of numbers that I know that there is a relation between them for congruence conditions. But you can actually do that and come up with a constant that fixes this problem, and some proportion of this asymptotic will be twin primes. And this is something that was done by Hardy and Littlewood. They have a much bigger conjecture called the prime constellation conjecture, that if you have we'll talk about primes constellations, but in any case, they have a very precise conjecture for how many primes there should be up to x. And you can come up with this formula in a couple different ways, not only just sort of like from the heuristic of the probability of a number being prime. Okay, so So the conjecture, in fact, so it's bigger in that it's talking about k-tuples, admissible k-tuples. So for instance, p and p plus 2, there may be infinitely many primes that p and p plus 2 are primes. There are not infinitely many primes such that p plus 2, and p plus 4 are all primes because, well, that's impossible because one of the three will be divisible by 3. So there's only one such triple, 3, 5, and 7, right? So, but you can come up with other ones like 0, 2, and 4, meaning p plus 2, and p plus 4. There is no congruence barrier for those to be a triple of primes, and there should be infinitely many triples like that. So they come up with a conjecture for all possible constellations, all possible admissible k-tuples of primes. If there is no congruence barrier, then there should be infinitely many. And they give a formula, just like in the twin prime conjecture, for how many there should be asymptotic to that. And if you forget about the constant, then you can use our very basic heuristic that there should be, well, I'm talking about k numbers being prime. If I've removed when there may be dependence, then there is independence. And if there is independence, it should be that the probability is given by the kth power of the probability of one of them being prime. So that's how you should view that formula. Okay. Hard and Littlewood, they stated a number of conjectures. Another conjecture that they stated is the following. This is called Hard and Littlewood's second conjecture. For all n sufficiently large, if you fix a k, then pi of k should be bigger or equal to pi of n plus k minus pi of n. What that says is that if you look at how many prime numbers are there up to k, then look at blocks of k numbers later on, there should be less and less primes as you go along, or at most that many. Okay, and you can just think that the primes sort of like peter out, just get more sporadic, and then if you fix a length, then the very first k number there should be the most number of primes. That may not be true. It's sort of like thin at the beginning, but then if you move it a little bit, then there is a lot. But then if you go far enough, there should be just less and less and less. Why would we believe that? Well, we have our heuristic argument that says, well, what's the probability? How many primes are there up to k? Well, is the sum of those logs. What's the probability that how many primes are there from n to n plus k? That will be the sum of the probabilities. But as you move the n, those logs will go to 0. So that sum will actually go to 0. The sum on the right will go to 0 as n goes to infinity. So there should be less and less and less primes as you go in intervals of length k. So this is a reasonable conjecture, at least according to our heuristic of primes. Okay. Well, it turns out that Douglas Hensley and Ian Richards showed that one of the two conjectures is false. Either the prime constellation is false or the second conjecture is false. In fact, you can show that the first conjecture implies that the second one is false. Now, it's weird because they both look very reasonable. Like what if this is false? What does that mean? That there is going to be like intervals that you fix. So if up to k there is 100 primes, then there is going to be infinitely many intervals far and far and far away where there are more primes at the beginning. And so it's just a little bit bizarre that you're going to be able to pack a lot more primes infinitely often than in one interval early on. So here's how you prove that the first implies that the second is false. So for instance, there is an admissible k-tuple of 447 integers up to 3,159. If the first conjecture is true, then there will be infinitely many primes that fit that constellation. Okay, so those are primes that are in the interval from p to p plus 3159. for each one of those primes, then there is at least in the interval from p minus 1 up to p plus 3159, there will be at least 447 primes. But if you count how many primes are there up to 3160, it turns out there are 446. So if the first conjecture is true, then there will be infinitely many times where in intervals of length 3160, there will be more primes than in the first interval of 3160 numbers. Okay? So Harris will give you a tour of some software, and I would like you to try to find what this admissible k-tuple is. I haven't seen it, so just try to find it. And not only that, I would like you to explore whether this is the smallest such k-tuple. Can you find a smaller k-tuple that would violate this pair of conjectures of Hardy and Littlewood? I'm not sure that's the smallest one. So that's some interesting computational problem of trying to find these interesting k-tuples. Okay. I wanted to talk about Wieferich primes that came up before. So if p is a knot prime, then Fermat's little theorem tells you that 2 to the p minus 1 is congruent to 1 mod p. And therefore, 2 to the p minus 1 will be 1 plus a multiple of p modulo p squared, but that doesn't mean that p squared will divide 2 to the p minus 1 minus 1. And those are called Wieferich primes. So when 2 to the p minus 1 is congruent to 1, not only mod p, but also mod p squared, those are called Wieferich. These came up. These are, if you think like, well, that's a bizarre definition, it turns out you can prove at least a part of Fermat's last theorem if you assume that you don't have a Wieferich prime. So if these didn't exist, or there was only like 2, then you could prove essentially Fermat's last theorem. Okay, so this is where Wieferich was coming from when he started looking at these. Meissner found the first Wieferich prime, and the second one was found in 1922, and we haven't seen any other ever since. So, that is a computational bound that up to 4.9 times 10 to the 17, there are no Wieferich primes. So if you are going to find one, it's larger than that. Okay. So the conjecture is that there is actually infinitely many Wieferich primes, and there should be approximately log of x. And my exercise for you is to prove that, in quotes, using what we now know. Why is that the reasonable heuristic for Wieferich primes? And by the way, it is not so weird that we haven't found any more, because log x grows really slowly. It really takes its time. Was it log x or log x? Somebody said that it grows to infinity with dignity. Do you know, Keith, who said that? Well, somebody said that. I found that. That's very nice. But in any case, you see that log of 10 to the 17 is just 3.6. So at most, we would have expected to see maybe the third Wieferich prime by now, but it's okay. It's not an exact heuristic, so maybe we'll have to wait a few more millions and trillions of numbers before. Shanks said that it was log x or log x? Both. Okay. And last, but not least, so Sophie Germain, also related to Fermat's last theorem, also was looking at primes that such as p and 2p plus 1 are primes. So it seems there are infinitely many of those, so such as 2 and 5, 3 and 7, 5 and 11, 11 and 23, and so on. And there are the conjectures that there are infinitely many Sophie Germain primes. Nowadays, they're also interesting from the computational, from encryption. They're called safe primes or reason. And there are supposed to be infinitely many Sophie Germain primes. So